We've looked at a lot of homogeneous linear differential equations. Let's have a look at some non-homogeneous linear differential equations. Remember, a non-homogeneous equation is just one where the right-hand side isn't 0. So here's an example, y double prime plus 6y prime plus 9y equals sine of x. So here it's this sine of x part that makes it non-homogeneous. If this sine of x were 0, it would be homogeneous, but it's not. Now this particular differential equation has as a solution this function. So 2 over 25 sine x minus 3 over 50 times cosine x. I'm calling this y sub p. The sub p is for a particular. That's what the p is for. This is called a particular solution, which means it's just some solution. Now you might hope that as with homogeneous equations, there would be some easy way to come up with other solutions to this differential equation. So you might guess maybe we could multiply our particular solution by a constant. So maybe 2 times the particular solution is a solution. Or maybe we could multiply by, I don't know, any constant, or at least some constant. Okay, well, you should pause this video and try it. So take 2 times this particular solution, plug it into the differential equation, and see if it works. Okay, so I hope you did actually try that. What you found is that it doesn't work. So unlike for homogeneous equations, for non-homogeneous equations, if you multiply a solution by a constant, other than 1, I guess, you don't get a solution to the differential equation. So right away we can see non-homogeneous equations are quite different than homogeneous equations. Another disappointing thing is, right, we had a particular solution. If you add another particular solution, so if somehow you came up with a second particular solution, you might hope that this would be a solution, so a sum of solutions being solutions, but it's not. That's just not how homogeneous equations work. It's kind of disappointing. So let's see why this is the case before we come back to this example. Right, so if you have a non-homogeneous differential equation, it's going to look like this. Some linear operator applied to y is some function of x. And suppose you have a solution, a particular solution. Okay, so what happens if you multiply it by 2? So what about multiplying by 2? So let's put that into the differential equation. So L applied to 2 times our particular solution. We want to know, is this equal to g of x? Well, constants, right? We can move a constant multiple outside of a linear differential operator. So we get 2 times L applied to y sub p. We're checking, is this equal to g of x? But look at this piece in the middle here. L times y of p. Y of p is a solution to the differential equation. So right, if you put y of p into this differential equation, it works. And that means that L applied to y of p is g of x. So this is 2 times g of x. Is that equal to g of x? Well, not unless g of x is 0, which it's not, because this is a non-homogeneous equation. So this shows you that for any non-homogeneous equation, if you have a solution and you multiply by 2, you're not going to get another solution. The same kind of thing happens if you try to add 2 solutions. So if you have 2 solutions, y sub p plus y sub 2, and you add them together, do you get another solution? Well, distribute the L. You get L applied to y of p plus L applied to y of 2. But if both of these are solutions, then both of these pieces have to be g of x. And when you add those together, you get 2g of x. But that's not equal to g of x. And so adding solutions doesn't give you a solution either. So for non-homogeneous equations, there is a superposition principle like there is for homogeneous equations, but it works differently, so you do have to be careful. And here's how it works. So if you look at this differential equation, or this linear operator, y double prime plus 6y prime plus 9y, this is an example from a previous video. So just for a moment, let's throw away the right-hand side. So it used to be signed, let's throw that away. We get a homogeneous equation. This is called the associated homogeneous equation. And we know solutions to this differential equation. In fact, in a previous video, we saw that the general solution for this differential equation is c1 times e to the minus 3x plus c2 times x e to the minus 3x. Now I want to label this y somehow to indicate that this is a solution to the associated homogeneous equation and not a solution to the original equation. So to indicate that, I'm just going to put a little subscript c on this, and that c stands for complementary. So this is called the complementary solution or the complementary function. You have to be careful with the word solution because it's a solution not to the non-homogeneous equation. The complementary solution is a solution to the associated homogeneous equation. Okay, so now let's come back to the original non-homogeneous equation, y double prime plus 6y prime plus 9y equals sine of x. And remember, this had a particular solution, which was 2 over, was it 2? 2 over 25 sine x plus minus 3 over 50 cosine x. Did I have that minus sign up there? I did. Good. So, what does the complementary solution have to do with anything? Well, we can form another solution to this differential equation by taking our particular solution and adding the complementary solution. So this seems like a very strange thing to do at first. Why is it that adding a solution to a completely different differential equation gives you solutions to the non-homogeneous equation? Well, it's a lot easier to see if we back up and look at the general case. Okay, so let's take non-homogeneous equation with a particular solution y of p. So when we say that it's a particular solution, remember that means that L applied to y of p is g of x. Okay, also we have the associated homogeneous equation, which we get just by throwing away that right-hand side. So that's L of y equals 0. And this will have solution, which remember that we call the complementary solution, y sub c. And since usually y sub c will be some combination of a fundamental set like this. Okay, since it's a solution to the associated homogeneous equation, that means L applied to y sub c is 0, right? Because y sub c is a solution to the homogeneous equation. So what happens when you add these two? So now let's consider the particular solution plus the complementary solution. So let's see what L does to it. All right, well, we can distribute L because it's a linear differential operator, so it distributes. We get L applied to y sub p plus L applied to y sub c. but L applied to y sub p is g of x. And L applied to y sub c is 0. And so this whole thing is just g of x. But that means that y sub p plus y sub c is a solution, because it satisfied the original non-homogeneous differential equation. All right, so finally we have a recipe for coming up with new solutions to a non-homogeneous equation. So for a non-homogeneous equation, L applied to y equals some function d of x, g of x. What we need is a particular function, or a particular solution, and a complementary function. Remember, complementary function is a solution to the associated homogeneous equation L applied to y equals 0. Then all the solutions to the equation are given by just the particular solution plus the complementary solution. I should comment on, so I said all solutions are of this form, and that's true if you can apply the uniqueness theorem to this differential equation. And remember, that's usually going to be the case as long as all your coefficient functions are continuous and your leading coefficient isn't 0. So when I say all here, it's usually all if our theorem for uniqueness applies, which it does usually in most cases. So that's the superposition principle for non-homogeneous equations. Rather than just taking any combination of solutions, it's a particular solution plus the complementary function.